The path of a reaction and the effect of a catalyst. So we've been talking about the equilibrium constant, which describes how far a chemical reaction will go. It describes the balance of it. You can almost think of a teeter-totter. And which side of the teeter-totter is going to be lower? Is it the product side? Is it the reactant side? But it doesn't say anything about how fast the reaction is. So reaction rate is what describes the speed of the reaction, how fast it will get to equilibrium. Another concept we need to talk about is the activation energy, sometimes called an activation barrier. This is an energy barrier that needs to be overcome in order for the reactants to be converted into the products, for the reaction to occur. Activation energies exist for most chemical reactions. We talked about collision theory and how in order for two molecules to react, they have to actually collide with each other. Not only that, they have to collide with enough force. If they don't collide with enough energy, nothing happens and they'll just bounce off of each other. The amount of energy needed in that collision is related to the activation energy. What happens there is you've got enough energy in the collision that the existing bonds break, which allows new bonds to form. So a certain amount of energy is required. So this is another place where chemists like to draw little pictures. So this is an energy diagram. Here we have energy increasing up the y-axis and the reaction pathway. You can kind of think of that as time. As time goes on, what's happening. And so here we picture our reactants. Here we're reacting hydrogen and oxygen to form water. And so initially the reactants have a relatively high potential energy. That means there's a lot of energy stored in their bonds. Is hydrogen gas flammable and explosive? Yes, it is. Is oxygen flammable and explosive? Yes, it is. That is an indication of its high energy. Does water explode? No. Water has lower potential energy. There's not this potential for an explosion. What is an explosion? It's a sudden release of energy. And that energy comes from chemical bonds. So the reactants here have higher energy than the products do. When these guys run into each other in the right way, they will form water and release energy in the process. So this is an exothermic reaction because it had more energy to start with and it released energy and now the products are lower. But there's this hump in the middle that it has to get over. And this makes me think of miniature golf. So I'm going to draw a little stick figure here playing miniature golf. So here's my little miniature golf person and here's his golf club. This reminds me of the little humps in the miniature golf course, right? You have to hit the ball with enough force that it gets up and over, or it's never going to go in the hole. If you hit it just a little bit, it rolls partway up the hill, and then it comes right back to you, doesn't it? Nothing happened. No reaction happened. You have to hit it hard enough to get it up and over the hill. Once it gets over the top of the hill, what happens? It rolls down the other side. It never comes back up this little lip and comes back to you. And so these reactants, if they have enough energy to get over this hump, then they will go ahead and react and form the products. Okay? So if you have a higher activation energy, you need a larger or higher energy collision for the reaction to occur. Any questions? So if you have a reaction with a high activation energy, that hump is really high, it's harder to get the ball over a high hump when you're playing miniature golf, right? It's going to take you longer. If the activation energy is high, the reaction is going to be slower. How could we speed up the rate of the reaction? A catalyst, yeah. At a specific temperature, at a given temperature, so a catalyst is good. A catalyst lowers the activation energy barrier. That's like cutting the top off the hill. Makes it easier to get the ball over the hill if the hump is lower. How else could you get things over the hill, though? Hit them harder, hit the ball harder, right? Collisions in chemistry are the energy of the collision is related to how fast the particles collide. If we increase the temperature of the substance, what does that do to the motion of the particles? They move faster, right? Barefoot people on cold sand walk slowly. Barefoot people on hot sand run to the water, right? So you heat up your solution, you heat up your reaction mixture. The particles are moving faster. They're going to collide more frequently, and they're going to collide with more energy, and so that will increase the rate of the reaction. You can also increase the concentration. The more particles there are in that small area, the more collisions that you have. Not every collision will result in a reaction, but the more collisions you have, the more reactions you will have. So we can increase the concentration, we can increase the temperature, or we can use a catalyst. The catalyst lowers the barrier. So here's the hill analogy that your book uses. So trying to roll boulders off this cliff. First, you have to get them up this hump, right? You have to put in a lot of energy to push it up there. That's going to be a slow process. You can imagine that. A catalyst is like finding an alternate pathway around the hump. It's like, you're pushing over the hump, but actually if you just went a little bit to the right, there's a much lower hump to push over. Well, you could get things done much more quickly if you go the way that has a lower hump. So that's what a catalyst does, is it reduces the activation energy. It creates an alternate pathway, a different way for the reaction to occur. So here's the energy diagram. So the black line is the normal activation energy. The catalyst can cut that down pretty significantly. Now, more of the reactants that collide are going to have enough energy to get over the hump. Does that make sense? You guys aren't inspiring a lot of confidence here. Have you heard of enzymes? Okay. Well, enzymes are biological catalysts. They create an alternate pathway for the reaction to occur and speed it up. When you think about biochemical reactions, reactions in living organisms, many of those reactants are sensitive to heat. So you can't just heat the substance up to make the reaction faster. Your body says, well, we need to make this protein. We'll just raise your temperature to 200 degrees. No, that's going to kill you, right? So raising the temperature isn't an option. Many times changing the concentration isn't an option either. And so what your body does, and what all living organisms do, is they use enzymes to control the chemical reactions within their systems. So enzymes are biological catalysts used to speed up reactions. So an example is the hydrolysis of sucrose. So sucrose is a disaccharide. It's a glucose molecule and a fructose molecule that are bonded together. This is table sugar. When you eat table sugar, your body metabolizes it. And the first step is to break these two pieces apart. That requires a certain activation energy. It's not going to happen just sitting there. You put sucrose in water, and it doesn't hydrolyze all by itself. The activation energy is too high. If you heat it up, you'll increase the rate of that reaction, but if you heat sugar up too high, it can caramelize and burn. And so that's not going to work out very well. So your body has an enzyme called sucrase that lowers the activation energy and allows this hydrolysis of sucrose to happen at a reasonable rate at body temperature. The way it does this is the enzyme has what's called an active site. And so the sucrose molecule, here's the two pieces of it, and it's bonded here. It comes in and docks. It's almost like a spaceship docking, on the Death Star or something. It comes in and it just fits in here perfectly and it goes, right? But when it does that, this bond is stretched. Because of how the two parts of the molecule fit into the enzyme, it puts some strain on this bond and weakens it, making the hydrolysis of it much easier to occur. That lowers the activation energy. So you think about, maybe cutting something, what gets easier to cut when you bend it? My analogy maker is broken this morning.
Like your saran wrap, when you stretch it and then you slide it.
Yeah, saran wrap, when you stretch it tight, it's much easier to cut than when you try to cut it all loose and floppy, right? It's kind of a different principle, but it's the same general idea. It gives us the same idea. This is stretched tight now. It's strained, it's weakened, it's easier to break. And so it will happen at a much faster rate. So your body uses this. And then the other cool thing about enzymes is your body can control the enzymes. And so, the more you learn about biochemistry, the more amazing it is about all the chemical reactions that are occurring in your body right now and the tight control that is maintained over them. It's just mind-boggling. And there's the end of the chapter. So what do you need to know about catalysts? You need to know that a catalyst lowers the activation energy and in doing so speeds up a reaction. That's pretty much it.